So, the second half of 9.2 is all about projection of vectors, and we only have one lesson goal, so this should be a fairly short lesson, is to find the projection of one vector onto another. And it sounds suspiciously similar to what we did yesterday, finding the component of one vector along another, and you'll find out that they're actually quite similar concepts. But before I actually dive into a projection, we have to do a little bit of background work. We need to talk about something called a unit vector, if my handwriting will let me spell it. A unit vector is simply any vector whose magnitude is 1. Right, and that's basically in math, that's what the word unit means. It involves somehow the number 1. And that's it. That's the only criteria. I don't really care the shape, the size, the color, its like, its dislike. The only thing that makes a vector a unit vector is that its magnitude is 1. So any vector can be a unit vector, but one of the more famous ones are the unit horizontal, unit vertical vector, the i's and j's we've been working with. Again, I by definition is the vector 1, 0, and j by definition is the vector 0, 1. Right? But as I said, any vector can be, man, I can't spell tonight, unit vector. But of course, the bigger question is how, because if unit vector is very specific, the magnitude has to be 1. Go ahead and try right now. Just draw any random vector you want, a line, an arrowhead, and I will bet money that no matter what system you pick, every unit is 1 inch, every 5 centimeters is 1, every 2.8 millimeters is 1, whatever. It's very hard to just randomly draw a vector as a unit vector because its magnitude is inevitably going to be some number other than 1. So how can I claim that any vector can be a unit vector? Well, it's very easy, right? Every single vector, I just drew a random vector, is made up of 2 components. Or rather, has 2 attributes. I don't want to use the word components because that sort of implies horizontal and vertical. It has a length, magnitude, and a direction, theta. Well, if the only thing that makes a vector unit vector is that this length here is being 1, well, for any given number, it's very easy to create the number 1. You simply divide out itself, right? How do I change the number 5 into the number 1? Divided by 5. How do I change the number 12 into the number 1? Divided by 12. How do I change the number 2.87 into the number 1? Divided by 2.817. I think that's what I said. So that's very easy. So the way you make any vector unit vector is simply just divide it by its magnitude. So any vector can be a unit vector. How? All you simply need to do is to divide out its magnitude. And let's go ahead. Let's see. All you simply need to do is divide out its magnitude. So let's go ahead and just sort of formalize that idea. For any vector u, if I take its vector and divide out its magnitude, is guaranteed is a unit vector. Right. So for any vector, if you divide out its magnitude, it's guaranteed to be a unit vector. Now, why do we care about unit vectors? What is its purpose? Right. The idea is that unit vectors are used to impart unit vectors are used to impart direction to any length. For you people who like biology, a unit vector is sort of like a stem cell. It can basically be put with other things to be anything you want while imparting a particular attribute, and that attribute is the direction, right? So if you had a number, but you wanted that number to be pointed in a specific direction, you just multiply it by a unit vector, because what it does is it augments or it rotates by the direction of the unit vector, but it doesn't change the magnitude because, again, the magnitude is 1, so it's essentially multiplying by 1. So unit vectors are really, really good if you want something in a particular direction. Now, why does that all matter? Why does that, how does that relate to today's topic, which is a projection? Right? So a projection is similar to a component. The only thing that's different is a component is just the length, and a projection is an actual vector. So let's draw the diagrams that we saw yesterday. So I'm going to draw two random vectors. Let's call that u, and let's call that vector v. If we imagine a sun here, this length here is the component of u onto v. But if I don't want just a length, vector u, vector v, but I want instead the actual vector, we call that the projection of u onto v. So that's basically, it's a very subtle difference. A component is just an amount, it's just a number, while a projection is a vector. Not only that, it is a vector that's pointed in the same direction as v. So the idea is that the projection of u onto v, it's the same notation, is simply the component of u onto v in the direction of vector v. That's the main idea. So, that is our dilemma. So how do I impart v's direction onto the component? What do you know? That's the job of a unit vector. So here is the idea, and here's the formula. To impart vectors v's direction, onto the component of u along v, simply multiply by v's unit vector. Right. That is the sole purpose, the sole job of a unit vector, is to impart the direction without finagling the magnitude. In other words, projection of u onto v is simply the components of u onto v times the unit vector in v's direction. Fortunately for us, we do have formulas for each component. As we discussed yesterday, the component of u along v is simply the dot product divided by the magnitude of v times, and as we discussed before, the unit vector in v's direction is just the vector v divided by the magnitude of v. And of course, we can multiply straight across, and we get, now here, you're going to be very subtle here. This right here is a dot product. This right here is just regular multiplication. They're technically not the same, so we can't combine them. But we can certainly combine the denominators because it's just regular multiplication. So this is typically written as u dot v divided by the magnitude of v squared times vector v. That is typically the projection of u onto v. So that is the formula, that is the official fancy schmancy textbook formula to find the projection. One thing to note though, for any two vectors, again, I'm just going to draw our usual picture. Here is the projection of u onto v. The projection of u onto v will always be a horizontal component of vector u with respect to v's direction. What does that mean? That means we should be able to find another vector that's orthogonal to it that adds up to vector u. Just for notations purposes, let's call the projection vector u sub 1 and the vertical component vector u sub 2. Okay. It is always true that u sub 1 plus u sub 2 will always equal the original vector u, where u sub 1 and u sub 2 are orthogonal. Always true. That means if we wanted to find an orthogonal vector to the projection, we don't have to do fancy cosine formulas like we did yesterday. It always follows this simple algebraic expression. Because if you do a projection, which is u sub 1, you'll have that quantity. They'll obviously give you the original u. So to find u sub 2, it's just a simple subtraction problem. U sub 2 is always the original vector minus the projection. In other words, vector u sub 2 will always equal the original u vector minus the projection. The original u vector minus the projection of u onto v. That's going to be important because the instructions are going to sound pretty funky. Let's go ahead and write this as a clear, crisp formula box, and then we'll do an example here. So this is the vector projection of u onto v. So we say the projection of u onto v is given by this formula here. I'm just rewriting the formula. U dot v divided by the magnitude of v squared times vector v. If the vector u is resolved into u sub 1 and u sub 2, where u sub 1 is parallel to v and u sub 2 is orthogonal to v, then we have these definitions. U sub 1 will always be the projection, and u sub 2 will always be the original vector minus the projection vector. Right. So if there's one thing you want to put on your highlight in your notes, put on your index card, it's this concept and this concept, right? This will give you a way to always break apart one vector into two orthogonal pieces, where one of those orthogonal pieces is parallel to a reference vector, vector v. The instructions will basically be simple and straightforward. So here's an example. If I give you two vectors, say vector negative 2 comma 9 and vector negative 1 comma 2, I'm going to ask you to find the projection of u onto v, and this is how the instructions will say, resolve u into u sub 1 and u sub 2, where u sub 1 is parallel to v and u sub 2 is orthogonal to v. The instruction is going to sound super duper fancy, but remember, one of it will be the projection, and the answer in A, and the other will be a subtraction. So let's go ahead and solve this. Letter A, I'm just going to straight up follow the projection formula, because that's exactly what they ask you. So the projection of u onto v is going to be the dot product. So x times x plus y times y divided by the magnitude of v squared. Now remember that the magnitude formula has a square root in it. Well, if you square a magnitude, it's basically Pythagorean theorem without the square root. So I'm going to ignore the square root and just go x squared of the v plus y squared of the v. Then I have to multiply it by vector v. Right. So we have, just do some math here. What is that? 2 plus 18 is 20 over 5 times vector 1 comma 2. So that is going to be 4 times negative 1 comma 2, which is very easy. Distribute the 4, negative 4 comma 8. So that right there is the projection of u onto v. That is the precise vector that will make up one component of u that is in the same direction, parallel to vector v. So what part B is basically asking you is, okay, find the other components, right? If you found the component, if you found one vector that makes up vector u, find his orthogonal buddy. And then to do that is quite simple. So we've already found u sub 1. U sub 1 is automatic from the projection, negative 4 comma 8. So that's done. U sub 2 will always be the original vector minus u sub 1. Well, the original vector u was negative 2 comma 9, and then I'll go ahead and subtract u sub 1, which we found out was negative 4 comma 8. So this is what? Negative 2 comma 9. I'll go ahead and distribute this negative. So it's a plus positive 4 comma negative 8. And then combine like terms, that's going to be 2 comma 1. So I can guarantee you that if you were to graph these two box vectors here, they will be 100% orthogonal to each other, plus this one will lie on exactly v, and this one will be perpendicular to v. By the way, I chose this example nicely from the textbook with that had whole integers. More likely than not, though, when you do these projections, you're not going to get nice, neat numbers. Just leave it in fraction form. You're just going to have to do a bit of math with fractions. Not too bad. So there you go. That's it. That's just the latter half of 9.2, just projections. Basically, a projection is the same thing as a component, but with a unit vector tacked on. A component is just a number. It's a length, whereas a projection is an entire vector, length with direction. Go ahead and give it a shot. Hopefully it's not too bad, and of course, feel free to email if you have any questions.